So Krista Amori asked that same question on the GitHub issue tracker. So if people are not used to GitHub, that's sort of the way that I'm trying to encourage people to use to ask questions that have some generality. And I do that because it's searchable by other students, and it's, it's a way for me to put up responses that might be useful to other people. And then for that singular issue, let's see, were you getting it? You were probably getting it when you tried to do the SD report, or do you know?
So I'm getting it. So I can fit the data set. My third model includes a covariate or a bunch of covariates. Either way, I'm getting the same error. When I fit it with the actual data, it fits just fine. When I try and fit it with simulated data, it gives me the error, whether it's the correct model or not.
Totally.
And the other two models fit all the simulated data sets fine.
So it sounds like you got pretty far.
Yeah.
I was saying that the homework I'm extending until to be due at the beginning of next Tuesday.
Oh, okay.
Yeah. So people have. Grant was saying that his email got bounced when he tried to send in the homework. Including him, I've only gotten 4. I don't want to call people out about who I have gotten from and who I haven't, but so make sure to check for any bounced email, and maybe Jay and I will respond on that email to say we got it. So if you don't get a response from us by the end of the day, you should assume that there's a problem. Okay, so we were talking about the singular. So what does singular mean? Like when would we refer to something being singular?
When it's less than full rank.
Yeah, so if you have a matrix has a rank, and what is the rank of a matrix?
The number of linearly independent columns.
Yeah, so one way to check it is if you do an eigen decomposition and you look at the eigenvalues. If it's full rank, every eigenvalue is non-zero, and if it's reduced rank or singular, one or more of those eigenvalues is essentially 0. So like 1 trillionth or something. And so we haven't talked about the Laplace approximation yet, and we will today, but there's 2 places where a matrix comes into what we're doing. And both cases, it needs to be full rank. So one of them is in the Laplace approximation. You want to ask a question, Nick?
No, go ahead.
One of them is when doing the Laplace approximation, we've got a matrix of second derivatives of the random effects. And then we're going to need to invert that matrix. And if it's not full rank, we can't invert a matrix. This is about as much linear algebra as you need for the class. So the Laplace approximation fails if that matrix of second derivatives of the random effects is not full rank, and that's one error you can get. Another one you can get is when you're calculating the standard errors, you calculate another matrix of second derivatives that you invert to get the standard errors, and we were talking about that last week already. And if that matrix is singular, then you can't get any of the standard errors. And so not seeing the exact error message you have, I can't say which of those 2 it is that's singular, but one way to do that is to try running the model without doing the standard errors. And if you get some message about it being singular or not full rank or something, then that's a problem with the random effects. And if you can estimate the model, get the MLE, but then you try to get the standard errors and that fails, then that's a problem with your fixed effects not being full rank. And if I had to guess from your description, I'm just assuming that one of the parameters is having no effect. One of the fixed effects has no effect on the likelihood, so the gradient of that is 0, which means that the rank of the Hessian would be 0.
Yeah, I'm confused because I've taken the exact same I took the design matrix from the fit that works
Yeah,
and used that.
totally,
The only thing I've replaced is the actual catches.
totally, yeah.
So I'm having trouble tracking it down.
Yeah, no, totally. And I'd be happy to, so like if you ask a question about Singular, I'll try to give kind of the general response, and then we get into sort of specifics, and that's where I'm happy to iterate code. But, it's hard for me to give kind of feedback if people are doing homework at the last minute, because almost every question I'll try to go back and forth a little bit before I actually look at anybody's code. And so, okay, so any other kind of big picture issues that people have? Yeah.
This is a really basic question, but I'm relatively new to TMB.
Totally.
I'm having a really hard time getting stuff out of it. So
Yeah.
I'm doing report, and then, one of the vectors or a value that we created
Totally.
in TMB, and then trying to do the model $sign report parentheses.
Totally.
But then it only has the objective function in there. It doesn't have anything else that I asked it to report.
Well, when in doubt, I would recommend doing like a hard restart of R every time you make changes to the CPP file. So one possibility is that you're changing the CPP file and then you're trying to recompile it,
Mhm.
but it can't recompile it because you've done the dyn load statement, which is meaning that it's trying to use the DLL that it compiled previously. And because it's using that DLL, it can't overwrite it. It's protected on your machine. And so, one of those errors that I've seen people have is where they'll make changes to the CPP, they don't download it, they try to compile it, it fails, and they don't notice that it had an error in the compile thing. And then they're like, oh, why didn't the change happen? So that's one possibility. I don't know. So that would be something we could look at.
Okay.
So there's a lot of stuff. Again, this class is sort of front-loaded with kind of logistical and statistical stuff, so that basically by week 5, we have covered basic time series models and basic spatial models, so that people have the kind of whole range of the class to think about for their project. And yeah, I apologize that there's sort of a lot of C++ learning people have to do. Anything else people want to?
Can I ask about the cross-validation part? I had 2 things. One, I don't know if anyone else is using R Markdown, but I feel like it's a nice, I like using it. When I was knitting the R Markdown, sometimes I'd get NA ends in places where when I was running it interactively, I wouldn't, and then I would run it again and it wouldn't be there. So I don't know what is up with that. I don't know if anyone else is seeing something similar. I don't know if it's like interaction with R Markdown and TMB. I've never used TMB before, so I don't know if that is something people know about.
Yeah, I don't know of any general R Markdown, R TMB issues, but I do know that, R Markdown, people often run through RStudio, and then it depends on the version of RStudio you have, but I don't know, I think that's a little squirrely.
Okay.
The big issue I usually see with people having trouble with R Markdown is that it runs it in its own process. The first thing is it runs it in its own process, so it starts sort of clean and doesn't generally use any of your variables that you've defined before. So it could be, I don't know if it's working sometimes and sometimes not. That's weird, obviously.
Yeah, and I would get like very different values for the, I don't know, I can't remember what the correct term is, but like the out of sample log, average log likelihood for data. What's the term?
Sometimes I use predictive score.
Okay. Yeah, I would get very different values for that, and like running the exact same code and like with the knit, so I know it's a hard, it's not like pulling in objects in my environment that existed before.
The other thing is sometimes TMB changes your working directory.
Well, yeah, so TMB shouldn't change the working directory, but I got used to using TMB back in the day when you had to set your working directory to where you wanted to compile and link the library. And I also find it helpful in distributed code to just have a single line to change the working directory, and that's the way that people get least confused about differences in naming. So anyway, so the scripts you'll see from me do involve changing the working directory.
So what's the option to not change the working directory? I didn't know that was even that.
Well, I thought that in theory, that TMB could allow you to specify a location for compiling and linking something without actually changing your working directory to it. But I think that was something that I thought somebody said and hadn't added since I started using it. So.
I think I tried that at the beginning of the class because that's how I like to code, and it didn't work for me.
Okay.
So I did it wrong.
Okay.
I just another general question about the predictive score. Can we interpret that as if we take the exponent of the negative predictive score, is that the average probability of each data point? Is that how it's interpretable?
Yeah, I mean, that's how I've interpreted it.
Okay.
Yeah, and you can look at the difference in average probability between two different models. But I'm not sure that metric is any more intuitive. I mean, it's hard, with any metric of model fit, you kind of need, something that bounds a really bad model and something that bounds a really good model. And then the metric is somewhere between the two. I mean, this is my philosophy of metrics of model fit. And so, well, I don't know. I mean, the absence of a perfect model, sometimes people look at a bad model, and then how much better the new model gets in terms of the log likelihood. But that's not totally intuitive to me why, if you improve the predictive probability of your out of sample data by 5%, is that a lot or a little? It's hard to say.
What's like I said, I feel like I was getting very weird sometimes values for that metric in particular. And I don't know if I should go back and try and figure out if I'm wrong or not for Tuesday for the next class, since I emailed you my homework, but like what's...
Yeah, I mean, it's up to you. I mean, as grad students, again, I'm not gonna, the goal, I mean, basically anybody who gets in the kind of full, component of the homework will get a pretty good grade. I mean, and in terms of why you might be getting really strange values for that, I mean, the data set we're fitting is really right skewed, so, but I guess you're simulating data. It's possible that the simulation is also really right skewed, and so occasionally you get some out of sample data that's really weird relative to the rest of your data, but I don't see why that would happen in the simulation.
Oh, I wasn't talking about the simulation part, I was talking about the part where we calculate we just like, whatever it is, the data that gets held out, we just calculate the log likelihood.
Yeah, and when you're doing that with the real data has some real outliers. So if you've got real outliers,
Okay.
sometimes those predictive likelihoods end up being really bad.
Okay.
Yeah. Any other? So we can come back to this at the end of the lab, but and Dan Ovando online has pointed out how you can load something without changing your working directory. But I actually don't totally understand what here : here means. So people can look and ask Dan if you have more questions.
Here's a package.
Here is a package?
Now,
Okay.
it's a recent package, so that when I think, I haven't really used it, but I think the idea is that when you send out code and you have your set working directory that's C users, Jim Thorson, you can instead use the here package to basically replace that so that it'll pop up on anybody's computer without, and work without being hard-coded to your user directory.
Cool, okay, that's interesting. Yeah, okay. Did you have another?
I just had a comment. I was wondering if anyone wanted to try and meet either like Monday morning or Monday afternoon to work through any last issues for homeworks for the next couple.
Sure.
Because I could book a room here at staff's if people are interested.
I couldn't be here, but I would be happy to like Skype in or something while
Okay.
you're doing that.
Yeah, we could set something up probably.
Yeah.
Yeah? All right, yeah. Sounds good.
Cool. Okay, so last class, last week we went through linear models, generalized linear models. Then on Tuesday we went through linear mixed models. Does anybody want to review Well, let's see. So what were some of the things that we were talking about on
You want me
Tuesday?
to talk about?
Oh, yeah, play. Thank you for the reminder. You want me to pull up this?
Okay, so since we are introducing the mixed effect model this week, today I'll be talking about this paper, which is global analysis of depletion and recovery of seabed biota after bottom trawling disturbance. Yeah, the reason I want to talk about this paper is because the mixed effect model we'll be focusing on in this class, it's in a spatial temporal context. But this particular study is just a meta-analysis. They don't model a spatial process explicitly. And so the idea is to bring up a couple issues which I think are important in the mixed effect model. So the mixed effect model, what we'll be talking about in this class is basically, using latent variables, which are treated as random effect in the model to account for spatial and temporal processes. So I'm going to present this paper like super fast because it's not in a spatial context. So, well, this, as I said, this is a meta-analysis. So basically, I think the objective is to quantify the impact of bottom trawling in the recovery of the seabed biota. So they collect a whole bunch of studies, trawling studies from different locations, as shown in this map. So there are two types of studies. One is experimental studies, which is kind of like before and after type study. And the other one is comparative study, which basically look at the impact of the bottom trawling across gradients of different addition frequencies. So we can see that the comparative studies are able to provide more representative estimate of recovery because they account for spatial extent, fission frequency, and temporal capabilities in fission activity. So they use the data collected from the experimental studies to estimate the depletion, and they use the comparative studies to estimate the recovery rate. Yeah, so let's jump right into the results. Let's first look at figure A and C, which shows the relationship between fission frequency on the x-axis and the community biomass, figure A, and community numbers, figure C. So this is the equation shows the mixed effect model they specify. So the response variable is log B over K, B is carrying capacity, B is either biomass or numbers, and F is capital F is the fission frequency, and B is slope. So by looking at a figure and equation, you can see they remove the intercept. Obviously, they force the relationship to go to zero, which sometimes can be problematic statistically. And well, if you can see the gray line, that's the random effect of individual study. So basically, they model the study as a random effect, allow the slope to vary per study. So as the gray line shows the random effect of individual studies in figure A and C, and the thicker lines are the mixed effect by different phenotypes. In figure B and D shows the number of years to recovery to 95% of carrying capacity as a function of recovery rate and the initial depletion. So just a couple of points that I want to make. Every time you do a mixed effect model, you might want to think a little bit harder about how to define the mixed effect model. If you want to want to treat intercept as randomly back or slope as randomly back or both. You don't want to consider the hierarchical structure of your system of your data, and which variable you want to treat as fixed effect, which variable you want to treat as random effect. And that thing is why we need the intercept. Because my personal experience is that you do want to always keep intercept in the model, because sometimes that ensure you have a zero mean residual. For example, if you have a model, if you have a spatial term in a model which is treated random effect, and then you remove the intercept, you basically move the systematic component to the random effect, which might bias the estimates. So, but Jim might have more erudite comments. Yeah, that's pretty much what I want to talk about today.
Cool. So for instance, does anybody, any thoughts on why the authors might have treated study as a random effect?
Sort of like we were talking about how there's certain things that are so variant and there's so many possible parameters that you couldn't tease them all out, so it's better to just sort of like integrate that out beforehand.
Yeah, right. So exactly. So relative to a model where you are treating each study as a separate fixed effect, you would probably end up with too little information for each individual study to figure out what the to estimate those parameters well. That's sort of what I'm hearing you saying.
Yeah.
Any other thoughts why it's useful? Like say you fit each study as a fixed effect. What might be the problem then? Besides having very little data from each study to estimate the relationship for each study well. Any other thoughts about why that would be difficult to interpret?
I know with like IHME, one really useful aspect of random effects is that you can predict, like using like the mean of a random effect, whereas if you have a bunch of fixed effects, if you have like a new unobserved study, it's hard to predict what the fixed.
Exactly. I mean, I think that's another benefit of a mixed effects model is it kind of automatically gives you inference about the prediction for each study, but it also gives you an inference about the kind of average across studies really easily. So, PNAS doesn't really care about what's the average trial effect in study X versus study Y. They just want what's the average trial effect, without really a lot of details. I mean, and so, that's my PNAS passion, sorry. So a mixed effects model automatically gives you that sort of summary of what's the average effect of trawling, but it still accounts for this variation among trawls. So it does this sort of like what we were calling variance partitioning on Tuesday, where there's some variance that attributes to variation among studies in the response, and there's some variation that attributes to variation within studies between data points that were collected by an individual study. So that variance partitioning, I think, ends up being really useful.
Don't we often use like vessel effect when looking at something as a random effect, also for similar reasons?
Yeah, right, exactly. So, and this comes back to what we were talking about how you could break a process into a bunch of smaller pieces. So sometimes when you do that, you end up with some benefits, and sometimes you don't. And I'm not going to really get into that here, but when we do sampling with contracted vessels, oftentimes one vessel is noisier or rolls more with bad weather, and so if there's a wind and it tries trawling, the trawl gets kicked off the bottom. Or one vessel might have a captain that's really risk averse versus risk prone. If you're doing health studies, and you're doing an, immunization study, like some doctors might be more or less likely to kind of have other protocols kick in and not use an experimental treatment. Some hospitals might have a different population with different kind of background rates of other things that are confounded. So there's all sorts of ways where, an experimental design ends up with multiple things that contribute to it.
So it's like sucking up kind of like between subgroup variance for factors that you can't account for, don't know.
Exactly. So one of the origins of mixed effects models was Fisher, and Fisher, besides being really into eugenics and sort of repugnant that way, he kept getting in fights with Pearson, who was his mentor, and basically got expelled from well-respected statistics, and so he was like banished into agricultural statistics. And you get all of these agricultural statistics studies with split plot designs where he would test out one crop or another in different parts of a field, but he can't control what the difference is among those fields. And so he developed mixed effects as a way of dealing with like, oh, if you do this A versus B test in that part versus this part versus this part versus this part, there's some part of that design that's random that can't be controlled. And so he would partition the variance into the treatment effect versus this background plot. So that was one of the many origins of mixed effects models. Okay, so I've been rearranging this slide over and over this morning, and I still don't think I have it in the shape I want, but, so sorry that I'm doing this, but, so the bottom line that we'll hear about today, and we'll derive this in a second, is that we want to calculate the likelihood, the log likelihood of parameters given some data. And we want to do that because if we maximize this with respect to the parameters, we get a good performing model, we get the maximum likely estimate, we know the benefits of that. However, a lot of times we can't compute that directly, and so we introduce these random effects or augmented data, and we have to integrate them out to get back to our likelihood that we want to deal with. So that's the explanation for this definition here. And the Laplace approximation is this second piece that you guys won't have, well, you probably won't have seen before, where we approximate this integral by calculating its probability at the maximum of it minus this h. And h is called the Hessian matrix, and we're already talking about it in the responses today. The Hessian matrix is the matrix of second derivatives of this around the maximum for epsilon. So basically this is saying that we can replace an integral, which is really difficult to do, with a maximization problem and this matrix of second derivatives. And Hans Gauck, I think, is the person who was first to realize that, Hans is somebody who some of us know in fisheries. He was the first person to realize that we had this software that was doing automatic differentiation. And so it's really cheap for us to compute this matrix of second derivatives. And so with the tools that we're already using, we can do this Laplace approximation really efficiently. So he figured that out sometime in the early 2000s. He developed ADMVRE, which was published in 2008. And then that eventually inspired, Casper Christensen to come along and redo it, and that's what TMB is. So I think we can kind of be proud in fisheries that, we figured out this sort of interesting use of automatic differentiation that, Google and people are now sort of like rediscovering with TensorFlow. Suddenly there's a lot more money behind this. But okay, so the intuition about how this works, I think, is all about trying to integrate a curve. And so it's easiest to plot this with a one-dimensional curve. And in this case, I'm going to plot a bunch of chi-squared distributions. So a chi-squared distribution is it's a standard probability density function. And any PDF has an area under the curve of 1. That's what probability integrates to 1. And that, so that's maybe intuitive. I'm sorry. So this dotted line was supposed to be at 0. I guess it's at 1. But the chi-squared distribution has a single input, which is the degrees of freedom. And so we can generate a bunch of different curves by changing the degrees of freedom, and we know that the integral of this should be 1, no matter what the degree of freedom is. That's why it's a useful example. And so if you didn't know the math of it, you didn't look it up on Wikipedia, and you were curious what the area under this curve is, what the integral of this density is, how are some ways that you might calculate that density?
Taylor series?
So Taylor series expansion, and that's how we'll derive the Laplace approximation. Are there any other ways that people might do it?
Riemann sums?
Riemann sums.
Wait,
I
that was
don't know.
like where you just like make a bunch of boxes.
Oh yeah, like the variance on like a trapezoid method, or yeah, exactly right. You've obviously taken calculus more recently than I have. That it's like there's like a bunch of good. I mean, there's people have spent 400 years at least figuring out how to do integrals. My favorite, and you'll see this if you look at the script how I plot this, I just evaluate the function for all values of the x-axis and sum that, and then divide by the width of those. So I guess it's essentially like a Riemann sum. Or you can take samples from the function, and that would get you to something like, Monte Carlo sampling. The Laplace approximation, intuitively, what the Laplace approximation does is it takes a normal distribution and sets up a normal distribution with the same standard deviation as the curve. So if you look at the peak of every one of these, well, it sets up a normal distribution with the mode at the same point as the mode of this curve, and the peak of it at the same point as the peak of this curve, and the standard deviation the same as the standard deviation of this. Well, technically, sorry, that's a bad way to say it. It's setting it up where the second derivative of this is the same between these two curves. So if you kind of squint and look at it, up here, these should be the exact same curve. At the peak, the red dashed line and the black line are the exact same curvature. And Laplace was the first, I think he was the first person to realize that if you approximate one function with a normal distribution with the same peak and the same mode and the same curvature, and then just read off the integral of that normal distribution, it is a good approximation. So in this case, the true integral is 1, and the approximation from the Laplace approximation is 1. I think that's actually right. That's actually surprising that it would be exact to the third decimal place to me, and that's the problem with doing this at the last minute. Well, I think that's true because I did it separate ways. And this is why nobody should do their homework right before the class is due. Yeah, so the approximation in this case is given almost exact answer the integral of this curve. And the benefit of that is that the normal distribution, all you need to know to get the integral of the normal distribution is you need to know the peak of that normal distribution, and you need to know the standard deviation of that normal distribution. If you know those two, then you know the integral. And so the Laplace approximation is all about figuring out what's the peak of this curve, and what's the standard deviation of that curve, or what's the curvature, what's the Hessian matrix. And then you plug that peak and that Hessian matrix into a normal distribution and figure out what the integral of that normal distribution is. So does that make any sense kind of intuitively?
But shouldn't it, since it's the normal distribution's a PDF, it integrates to 1?
Well, except the peak is matching the peak of the chi-squared. So that's the key.
Okay.
I'm gonna double check the calculation of the integral of the normal distribution later, but, or I could do it now, because I'm kind of obsessive. Yes, that makes a lot more sense. Yeah, okay, so there's the typo. So sorry about this. So the approximation is not exact, which makes a lot more sense. But it's still really good. So in this case, if you look at the area under this red curve, the integral is 0.92. This is what I was expecting to see, where the approximation, the chi-squared distribution is a nice example because we know that the chi-squared distribution, as the degrees of freedom gets larger, we know that the chi-squared distribution approaches a normal. And I'm not going to go into why that is, but people could ask later. And so it starts out this really right-skewed curve, and then as you get a higher degree of freedom, it eventually looks a lot like the red curve. And so as the chi-squared gets closer to a normal distribution, this approximation gets to be 0.994. You know, this approximation becomes exact whenever the underlying curve you're approximating is actually normally distributed. And when the underlying curve departs from a normal distribution, this approximation is worse. So like 0.92 up there is a worse approximation. Yeah.
I have a dumb question. The curve that like practically we're fitting out like in the example of chi-square is the distribution of the log likelihoods. So you're saying as the shape of the log likelihood deviates from the normal, then the Laplace approximation does worse?
Yeah, I mean, so the Laplace approximation applies to any curve, but how we're going to use it in this class is for the probability of the random effects given values of fixed effect. And so if the distribution of if the joint log likelihood with respect to the random effects is normally distributed, then the Laplace approximation is exact.
Is it possible to have a sense of when that assumption breaks down, or is that something that comes with time, or is that just like so?
Yeah, so there's a lot of discussion of that. I mean, that's basically the central question in using the Laplace approximation. And Casper Christensen has added a function called check consistency that I don't know how it works. So people keep pushing, coming up with wacky solutions. So that's why I got into MCMC sampling in the first place. I would fit a model with the Laplace approximation, and then anytime I would just fit it once with MCMC and see how bad that approximation is. We also went down this route of doing importance sampling, and that wasn't working. So we've spent like six years, me and others have spent time trying to answer that question. And there's a new feature that I have not tested. Okay, so the next question, so this is supposed to be sort of, I mean, I think this is pretty intuitive that if you match a function, if you have a function you want to integrate, and you take a normal distribution with the same peak, the same mode, and the same curvature, and integrate that normal distribution, that's a good approximation. And that approximation becomes exact when the curve you're approximating is normally distributed. And I think that's all, to me, that's all intuitive, but maybe it's because I've used this a lot. For other people, they want to see a derivation of how that works. And so that derivation can basically be derived from these two different rules, which I think, again, have some intuition associated with them. So I refer to this as sort of factoring, the axiom of conditional probability, where you break a joint distribution into a marginal distribution and a conditional distribution. And then the law of total probability is how you go from the joint back to a marginal by integrating across some other stuff. So those two rules are all you need to derive a marginal likelihood. Let's see, but shifting gears a little bit, this is going into this sort of the Taylor series expansion of this joint likelihood. So, so this is the joint likelihood of the fixed effects and the random effects given the data, and that's or it's the log of the joint likelihood. Sorry, so it's and if you factor that into this conditional probability and this marginal probability, where theta 1 and theta 2 are the hyperparameters and the other parameters, like we talked about. And then if we do a Taylor series expansion of this, the log of the joint likelihood, this is the second order Taylor series expansion. So we expand, you can expand it around any vector of random effects. And this statement is true by Taylor series expansion. But if you evaluate the Taylor series expansion at the best value of the random effects given your fixed effects, if you maximize that joint likelihood with respect to your random effects, that means, and call that the epsilon hat, your estimate, your prediction of epsilon, that implies that this derivative of epsilon, the derivative of the log likelihood with respect to epsilon is 0. And so that means this term drops out. And so we end up with the joint likelihood here can be approximated as e to the log joint likelihood. That's the definition of logs. And we can approximate that by plopping in this Laplace approximation here. And so the key to this will end up being that this looks a lot like the PDF of the probability density function of a normal distribution. So essentially, we're going to massage this right-hand side to look like the probability density function of a normal distribution. That's what we're going with this. So here I'm just reiterating the bottom of the last slide. We can integrate both sides, and we get the integral of this. This is a constant because we've estimated it, so we can pull it out in front. And the normal PDF looks like this, whereas this is, let's see, I don't want to do this a little bit.
Hey, Jim.
Yeah.
You may want to use your PowerPoint laser pointer for the people on.
Yeah, I'm sorry. Somebody said that last time too. How do I use a PowerPoint laser pointer?
Go to your,
Pointer options.
yes,
Laser pointer.
there you go.
So, and then I just like, okay. So, thank you. The key here is that this matrix of second derivatives, the second order Taylor series expansion, is equal to the Hessian of the normal distribution. And this deviation squared you can rewrite on the right-hand side and the left-hand side. And we've got this over 2 thing that goes in here, and it matches everything on the right-hand side of this normal distribution. The key is that the left-hand side of this this whole normal distribution integrates to 1. We're just taking everything after the x part, after the exponentiating, and we're dropping this normalizing constant in the front, and we're replacing it with the evaluation of the joint likelihood function. So, long story short, we can do a Taylor series expansion, we can get the matrix of second derivatives and invert that, and that's equal to the variance of a normal distribution that we use to approximate the function that we want to integrate. So a worked example of that, this is how I did the chi-squared example that I just showed you. If we have a random variable x that's chi-squared distributed with degrees of freedom k, then the probability that data equals that random variable is proportional to this, and there's some stuff on the bottom of this PDF too that I'm dropping out, so that's what I'm saying, it's proportional using this proportional sign. We can define the log likelihood as the log of that, and so if we take the log of that top function, we get this thing. If we take the first derivative, I think I did this, I double checked this in Mathematica online because I'm always paranoid that I will make stupid mistakes. And then the second derivative is this. And so if you solve for the mode of this, that's the location where the first derivative equals 0. So if we fix this equal to 0 and solve, we see that the mode of the chi-squared distribution is the degrees of freedom minus 2. And that, I'll, again, for fear of making a dumb mistake, that confirms what's on Wikipedia. And the second derivative around that estimate is equal to this. And so if we invert this second derivative, we get the variance of the normal distribution, and we can plug in the mode of that normal distribution here for the mean of it. And so what we're saying is that we can approximate a chi-squared distribution with a normal with mean equal to degree of freedom minus 2 and the variance of this. And so if I plot those normal distributions using that mean and variance, that's what we're showing here in the beginning of this. So anybody want to summarize what this derivation suggests again, or what we've seen visually? If somebody was going to ask you, what is the loss approximation in a sentence, does anybody want to take a stab?
Using a normal distribution to approximate a curve
Or-
in very basic language.
Yeah. And so if you were going to add one more sentence, how do you get what is the standard deviation of that normal distribution? Or what's the variance of that normal distribution?
The inverted second derivative.
The inverted Hessian matrix.
Yes.
So the idea is the second order Taylor series is kind of twisted into a normal distribution, and we can solve for that.
Yeah.
Okay.
And we know the integral analytically of that, given the mode of it, and the peak of it, and the variance of it.
Is there, I'm thinking like, I kind of want to like do this by hand so I can like.
Totally. And that's why I did the chi-squared originally. That's the, so yeah, I encourage you to take a different distribution and do it by hand.
Okay, cool.
Yeah, and given that intuition, the third sentence about the Laplace approximation, given that intuition, where are the cases where the Laplace approximation might break down?
Heavy skew.
Yeah, anything where the normal distribution is poor approximation, where the first, second, and the 0th, first, and second moments of the normal distribution are really different. So anything with a lot of skew, kurtosis, anything where you need higher order Taylor series expansion.
Could you extend this out to do higher order Taylor series?
I asked Casper that at a meeting. We were at at the Kappa meeting, and he said that he said that somehow the algebra would end up becoming way more complicated. I don't know. I haven't ever tried it.
So I know the in-law package uses, I think, at least one more, and this might have been their big thing, because they actually essentially fit a skew normal.
Huh, okay.
To do the integral.
That's interesting. Yeah, I know Inlet has a bunch of different options for how to do it, and then you can also do quadrature. So you can take the Laplace approximation and then use that as the starting point for other more complicated methods. So you could use that to define a quadrature grid and then do that. Inlet has an option for that. TMB was exploring using that as the sampling distribution for sampling importance resampling. You can use that as the proposal function for MCMC. And that's something that we haven't ever followed up on, but it would be fun if anybody was interested. That would be something where you could start an MCMC sample from the Laplace approximation with a fixed seed and then optimize that. So this is an active topic of research, is how to refine this Laplace approximation. INLA probably goes down a different pathway because they're not using derivatives. They don't use automatic differentiation from what I did when I last checked. So we have a sort of a different constraint on how we solve this than they do.
So takeaway I'm getting from this is then, if we're doing random effects in TMB, anything non-normal we want to avoid, or anything that's like, like a gamma random effect or something like that.
Well, so it's specifically, it's not just the distribution of the random effect, it's the distribution of the log joint likelihood with respect to the random effects.
Okay.
And we'll see an example here so for instance, if you have a normal, if you have a linear mixed model with a normal distribution for your data and normal random effects, that's guaranteed to have a normally distributed joint log likelihood. And so in that case, the Laplace approximation is exact. In a minute, we'll look at code where we use a generalized linear mixed model with a Poisson distribution, and that is not guaranteed to be exact, but we'll see that we end up with good estimates that match those that we get from R. So my kind of hand wavy, I'm not being a statistician, I just usually use the Laplace approximation without doing extensive theoretical confirmation. I do MSDMC to confirm, but leave it at that. Different people use it differently.
If you had a multimodal distribution, can you use the Laplace approximation twice and then take out the overlapping area?
That would be really interesting. Yeah, so that's a great question. The multimodal models, the Laplace approximation does horribly because it'll just go to one mode and approximate that, and it entirely ignores the other mode. So multimodal stuff is where you need, well, in my toolbox, I use MCMC for those. That would be interesting to try to do some like multimodal thing. The problem would be making sure the optimizers keep them separate. So like you wouldn't end up with them both in the same thing, or I don't know. So I'm not totally, yeah, it'd be interesting though. Is there any other, so this is about as, this is my, this is basically a whole class that I want to dedicate to having people have some intuition about what the Laplace approximation is doing. Because we're going to use it in every homework, lecture, and lab from here on. Is there any other stuff that people want to talk about with this?
I have a quick clarifying question that was already asked. Can you explain again why the integral doesn't go to 1 if X is very basic?
Yeah, so
I still didn't.
So I'll just show it in my code. So the Laplace approximation, the Laplace approximation matches. The Laplace approximation is written out here, except I'm dropping the normalization constant for the normal, and we don't need that because it's a likelihood, and so we only care about it up to a proportionality. We can drop out constants in the log likelihood. And the Laplace approximation is equal to the evaluation of the function at the estimate of the random effects minus the half of the determinant of the matrix of second derivatives. And so we're basically plopping in, we're saying we want to use a normal distribution where the peak at the mode is the same as the peak of the function. And so here we can see that the red line of peak is the same as the peak of the black line. If you used a normal distribution without doing that, redoing that peak, that approximation would look like this. Can people see this okay? Where as it goes to normal, the peak is the same as the peak of the black line, and the approximation still works. But if you don't sorry, I'm pointing again with my finger and not the pointer. In the top left panel, if you use a normal distribution that integrates to 1 without redoing that peak, the peak of it's higher.
I see.
Okay.
So the integral is different because we're basically dropping the density by 10%.
So in like picture space, what it's doing is basically like shifting up or down on normal distribution, so some density will be either above
Yeah, exactly, yeah. And so it's it's approximating a function with a normal distribution with the peak at the mode being the same as the peak of that function and with the second derivatives being the same. And that basically the integral is all about calculating, is essentially that, that difference up there. I'm not describing that last piece well, but that's why it doesn't integrate with one.
I think a little of the math is over my head, but I get it conceptually now.
Okay. Yeah. I'm trying to juggle sort of a graphical derivation, algebraic derivation, and a kind of plain language derivation, and so I'm kind of confusing myself as I go, and I apologize there.
What's a good distribution to start out with, you think, besides the chi-squared, to do this by hand?
Yeah, I mean, if I had more time, I would try it on some bivariate case. Like if so if you're willing to do, multivariate calculus, you could just do it on a chi, the product of a chi-squared and a normal or something.
Okay.
Chi-squared and f.
Okay.
Yeah. So again, we get to this bottom line where we're approximating the joint likelihood function. We're getting the integral we're getting the likelihood by integrating this joint likelihood function, and we're okay. Yeah. And then we approximate that joint likelihood function. We approximate that integral using the Laplace approximation. And to do that Laplace approximation, we have to maximize the joint likelihood function with respect to the random effects, and we have to get the matrix of second derivatives. And we have to, so here we're at a place again where we can see why we need, what was rank again? Why do we need full rank for the random effects?
Rank was the number of or the size of the eigenvector, right?
Yeah, exactly. The non-zero, how many non-zero eigenvalues it has. So if H, the matrix of, let's say that we've got some additional random effect epsilon, where the derivative of the joint likelihood with respect to epsilon is equal to 0. So then what's the matrix of second derivatives look like for that?
Wait, can you say that again?
Yeah.
Let's say you put in an additional epsilon, this is a vector, epsilon. Let's say you put in one additional term in epsilon that has no effect on the likelihood. You just put it into your model and didn't use it. In that case, any change in the value of epsilon has no effect on the likelihood, which means that the derivative of the joint likelihood with respect to that value is equal to 0. So what effect would that have on the Laplace approximation?
It's negative infinity.
Exactly. So the second derivative is also 0 for all rows and all columns of that element, which means that there's at least one eigenvalue of H that's equal to 0. And the determinant is the product of those eigenvalues, which means that the determinant here is 0, which means this is negative infinity, which means that it has, the Laplace approximation says it's never going to happen. It's infinite. It, just breaks your computer. So that's why, that's one place where rank comes in. If you put in a random effect and forget to put any distribution on that random effect, it'll break the Laplace approximation. And that's, that'll happen in the inner optimizer, and it'll say something about like something singular, something, because singular is math word for not full rank. Okay, so and then we talked about GLIMs on last Thursday, and then we talked about linear mixed effects on Tuesday. And so combining them, this is sort of the plain English description of what a generalized linear model is. You specify a distribution for your response variable, your data. You specify a function for the expected value, where G is called the link function. or I'm sorry, G, in the inverse of G is called the link function. And then you have a linear predictor on the right-hand side. And a generalized linear model includes, I keep doing this, a generalized linear mixed model includes some predictors that are fixed effects. So in a lot of mathematicians use the term X and beta. Beta is the fixed effect and X is the covariance associated with fixed effects. Whereas epsilon might be a random effect and Z is the design matrix for your random effects. And this linear predictor includes beta, fixed effects, and epsilon random effects. And then the final part is you have to specify a distribution for your random effects. And so in this case, a generalized linear mixed model, typically we specify a normal distribution for the random effects. And that's a generalized model. Here, we already started talking about this, but I want to reiterate it so that we can estimate the standard errors of our fixed effects by taking the Hessian matrix of our approximation to the log likelihood. So we do the log likelihood, we do the Laplace approximation, estimate our fixed effects data, and then we can take the curvature of that as a measure of the standard errors of our fixed effects. And that's this matrix of second derivatives. And if we invert that, we get the estimated variance matrix, and the standard errors are just reading up the diagonals and taking the square root. So here's the other place where we need a full rank Hessian matrix. And why do we need a full rank Hessian matrix here?
Because we need to invert it to get a variance.
Yeah, so I keep bringing in kind of small pieces of additional linear algebra because we're getting into details of how this works. But I think this should be. We'll also deal with the Cholesky decomposition at some point in this class, but we're pretty much at the full set of concepts we need from linear algebra. So to invert a matrix, you need it to be full rank. And you can Wikipedia like matrix inverse if you want to read more about that. But if this Hessian matrix is not full rank, then there's no way to invert it. That's the point. And so what happens if you put in a fixed effect that has no effect on your likelihood?
You get the bomb of death.
You get the bomb of death. You get in ADMB it was the bomb of death. You get this like crazy error message that it was hard to figure out what it's going to. In TMB, if you put in a fixed effect and forget to do anything with it, so it has no effect on your likelihood, then you can still estimate the maximum likelihood estimate, and that theta, that parameter, will never change because the derivative of the Laplace approximation with respect to that parameter is 0. And so the optimizer will just never bother moving that parameter. So you'll get an MLE, and you'll be like, oh great, I have a model. But then you try to get the standard errors, and it'll blow up the calculation of the standard errors. And in the standard error function, we'll say matrix non-invertible. So this is the second place where that matrix non-invertible thing comes in. Just to, we talked about the inner optimizer and the outer optimizer. I probably should have a slide kind of reiterating that. Can anybody remind us what is the inner optimizer and what's the outer optimizer?
I think the inner optimizer is optimizing your random effects according to like a given set of fixed effects, and then once you have the optimal version of that, then it like tries to step your fixed effects, and that's the outer optimizer.
Exactly. Yeah, so it does the inner optimizer. It maximizes the joint negative log likelihood with respect to the random effects. Once it gets to that maximum, it can do this Taylor series expansion and drop out the gradient. And that's what we call the Laplace approximation. And then it extracts that Laplace approximation and its gradients and uses that to change the fixed effects one step. And that changing the fixed effects one step is one step in the outer optimizer. Then it changes those fixed effects, and then it does the inner optimizer again, changes the fixed effects one more time, does the inner optimizer again, changes the fixed effects one more time. And all of those times it does that changing the fixed effects, we call that outer optimizer. And so if you have a random effect in your model that doesn't do anything in the likelihood, will that blow up the inner optimizer or the outer optimizer or the standard errors?
The inner.
Blows up the inner optimizer because the Laplace approximation doesn't work. And if you have a fixed effect that doesn't do anything in the likelihood, will that blow up the inner, outer, or standard errors? Standard errors. We'll keep saying these concepts over and over again. We're covering a lot of material. This will keep coming up over and over again. So one more piece of this, I'll come back to it in a bit when we look at the code. Okay, so we're going to pretend that we are doing a hierarchical model in which we have some group level average D sub j, and I'm using D for density, and it's log linked. So density follows this log normal distribution, and then counts C sub ij is Poisson distributed. So can anybody imagine where this model might occur in nature?
Counting rabbits.
Yeah, counting rabbits in a field or across fields. Yeah. Any other examples outside ecology?
We use this one for like small counts data all the time,
Yeah.
for just like diseases with low incidence.
Totally. Yeah, and how did we get the Poisson distribution in nature? When does that arise?
Independent counts at some rate.
Yeah, so it's essentially a binomial when you've got a lot of things you could be counting and the rate of each of them goes really low. So that, your example I think is really intuitive where you've got a lot of people and the rate of each person being infected is really low. So the way you described it, exactly. My understanding is like a lot of manufacturers use quality testing this way. So if you produce light bulbs and you want to make sure that the different factories you outsource are doing what they're supposed to do contractually, you might take your shipping container here and shipping container here, and test 1 out of every 100 of those and see how long they can last. Like I actually heard one time that the light bulb makers intentionally made sure their light bulbs didn't last too long because they wanted to replace them, and so there was some collusion originally in light bulb manufacturing that they would. I don't know if that's true or not, but I like that story. But so it comes up in industrial design all the time. Okay, yeah, and how many parameters are there in this model? Well, I'm going to say there's 2 because I want to call these fixed effects and these random the densities as random effects. And I only I try to use the term parameters just for fixed effects. And in this picture, I've got 4 different sites. We can also start seeing this sort of why you call this a hierarchical model. You can draw this directed acyclic graph. And this graph is actually a way of decomposing the joint likelihood. So you can define the joint probability of all of these via the conditional probability of the child given the parent. And so if you ever look at machine learning literature, they call stuff graphical models because they make a graph, a directed acyclic graph, where you can factor a joint probability into a bunch of conditional probabilities. You can always do that for a DAG, a directed acyclic graph. Okay, what's the mean across all of these sites? What's the mean density across all the sites in this model?
UD.
Yeah, well, so that's the median, technically, so the mean log density is that you technically have to do the, bias correction, so it's like it's e to the mu d plus the variance divided by 2. What's the variance of d? Well, I have to look it up on Wikipedia. The variance of a log normal is just like some mess, and I can always forget. What's the mean of counts across all sites and samples?
DJ.
Well, so that would be the mean for a given site, for sure. And then what's the mean of across all sites? Well, yeah, so it's e to the mu d plus the extra stuff. So the mean of the counts is the same as the mean of that, because we got a Poisson process for the counts. And then what's the variance? What's the variance of the counts? The point I'm trying to get at is this question: what's the variance of your counts from this hierarchical model?
Well, your variance of Poisson is going to be the same as your rate. So your mean rate plus the variance of your normal.
Yeah, exactly. So I should have started with a simpler example, because with this Poisson, we got a log link, and there's some like extra shit kind of running around here. But the point is that the Poisson has the variance of this hierarchical model is equal to the variance of your average for each site plus the variance, the variance of each count is equal to the variance among sites plus the variance within sites.
Oh, so it's just that transformed mu d plus the funky
Yeah.
log normal variance.
Exactly.
Cool.
Exactly. So in other words, it's the variance of that top line, which has some funky formula, plus the variance of Poisson. The variance of Poisson is equal to the mean of the Poisson, is equal to the e to the mu d plus the variance squared divided by 2. We could maybe we can work out a simpler example of that without the log link in a bit, if that's what people want to do. Remind me. So the remainder of the time would be walking through an R script and a CPP file for doing a generalized linear mixed model with the same model we were just looking at. And then the second homework will be fitting. It's the same thing where we have a simulation design where we fit a model, and then we simulate data from it, and then we fit a bunch of different models to that where they're either specified correctly or incorrectly, and we interpret how our variance partitioning changes when we specify the model correctly or incorrectly. So that's what the homework's going to be. And that homework will be due a week from Tuesday. So we can talk more about it next lab if people want. So we'll look at the code in a bit, but I think maybe we take a 5-minute break, 10-minute break. How long do people want to take?
I just gotta grab coffee.
Grab coffee out here. I want to grab coffee. I'll walk up with you. Okay, how about a 5-minute break?
Yeah, you wanna make coffee? Yeah, let's do that.
I'm gonna resume recording, and so the second piece of this is where we get to, well, I want to get through the R script and the CPP file. How quickly or slowly we go will be determined based on feedback from questions and such. And then, if we have extra time, we can also go through the homework one and actually look at people's scripts or whatever would be helpful. So, not knowing the here package. Let's see. So I'll cut this. as we've seen, I always set the working directory. I stall while I do zooming. I set the working directory. I'm going to use LME4 for linear mixed, or well, I don't know what LME4. It's linear mixed effects, I thought, but this is a Glenn because it's strictly a linear model. And then I simulate data for 10 sites, and just for the hell of it, I'll drop the number of observations per site to 3. The log mean of this is 10, the log of 10, and the log standard deviation is 1. And I call those log mean and log standard deviation because they occur in log space, so that's just my notation. That's my notational reminder that it's, that's my naming convention to remind myself that if I take the mean of the data, it's not equal to something called the mean, but that the log mean requires some transformation to get back to the actual mean. I then do bookkeeping where I figure out, I have an indicator saying that the first 3 observations belong to site 1, and then the next one site 2, and so forth. I simulate from a normal distribution what's the value of the RAM effect for each of the 10 sites. I simulate the mean of each site by exponentiating. So this is the mean counts, in this case, of each site, and I'm going to go back to the rabbit interpretation where we're doing some field sampling where we want to figure out how many rabbits there are per field for some reason. And then the data, Y, looks like this, where we've got 30 observations, and if we plot it using lattice, we can see that there's some variation among sites. So, for instance, these are all on the same x-axis, so we can see that like site 1 at the bottom left has kind of a relatively, well, maybe kind of an average density. Site 4 has a really high density. Site 5 has a relatively high density, and so on. So, there's this sort of variance decomposition that will probably, like Jay showed us, if this was trawling impacts and we had trawled for rabbits previously, I guess site 2 is heavily depleted and site 5 lightly impacted, and so forth. We can then fit a GLIM using the package just using base R. And so a GLIM, like we saw, just has a GLIM without mixed effects. The key that my mnemonic is that you can get kind of one source of variation for free. So you can do a fixed effects model and get one source of variation. And if you want to have multiple sources of variance, you need a mixed effects model for that. And so if you fit a GLIM, there's only one source of variance, and that's this Poisson distribution. And if you do a Poisson model fitted to this, you get the mean of 2.89, and you get this really tight standard error because you've got 30 observations that are all exchangeable, and you think that you've got a lot of data to estimate the mean number of rabbits. And as we'll see, that's not a very good estimate because we're neglecting the within group variance. We could also do, Nat brought up, with respect to what Jay presented, we could fit a fixed effects model to each individual site, and we'd get the average number of rabbits per site. But like we said, it's hard to then know what to do to summarize across those sites. We could take the average of those 10 site estimates, and that would be doing statistics on statistics. It would be hard to figure out how confident we should be about that mean estimate. And without doing that, it's hard to know what to say about, how many rabbits there are. Or you can do a generalized linear mixed model where suddenly it has two parameters that it's estimating. It has the intercept and it has a variance in the intercept between groups. That's what this is saying. And if we compare the GLIM, the fixed effects model with the random effects model, the random effects model gives a much higher standard error on the intercept. So let's just show that again. So the standard error on the fixed effects model is 0.42, and the standard error on the mixed effects model is, I'm sorry, it was 0.042 on the fixed effects model. Whereas it's 0.25, almost 6 times greater standard error in the mixed effects model. So why would we, did anybody have any intuition so far about why the mixed effects model has a higher standard error?
Because your sample size is technically smaller because there's correlation structure, right?
Yeah, so one way as with mixed effects models, there's always a bazillion ways to think about it. So one that I use all the time is that the data generating process has this within group correlation. And so the effective sample size is lower than the total number of samples because your 3 samples at site 1 are not really 3 separate samples, they're 3 correlated samples. So for instance, if you sampled 1,000 times at each site and you have 3 sites that you sampled and you're trying to estimate the mean of a whole universe that you didn't sample, what would be the sample size of that experiment? Well, it'd probably be closer to 3 than 3,000. I mean, you've got 3,000 samples total, but you're really only sampling 3 units from this population of sites. And so your effective sample size is always somewhere between the number of sites and the total number of samples. And that lower effective sample size causes the standard error to be higher. So, you can actually work out how to calculate the effective sample size, algebraically with simple models. And, I've done that for like the Dirichlet multinomial, but there's more work that people can do with that. Okay, and then we want to confirm that we're getting similar answers in TMB. So far, all the models we're doing are simple enough that we can do them in CAN packages and R. So in CPP, in TMB, we load the package, we compile it, we make a tagged list of the data, a tagged list of parameters, we specify which of the parameters, I'm calling it parameters, I should change the name of this. It's not parameters, it's a mix of fixed effects and random effects, which I've been calling coefficients. And which of those coefficients is a random effect. We then load, link the library, compile the object. And I wanted to talk about, we started out with John bringing up this error message we can get about a singular, something being singular. And we talked today, and hopefully people understand now that there's 2 things that could blow up your model if they're singular. One of them is the random effects during inner optimization, and one of them is the fixed effects during your standard deviation calculation. And so if I run obj $fun, obj $par, what part of the model am I doing there? If I run this, what have I just done?
Inner optimizer?
This was the inner optimizer. So this is the joint negative log likelihood. It starts out at 636 in iteration 1, and that drops down to 108. The maximum gradient component of that joint log likelihood with respect to random effects, the maximum gradient gets really low. Once it gets really low, we can do the Laplace approximation, which is why it triggers then, and we get a Laplace approximation of 115. Suddenly we're seeing a whole ton of these we're seeing a bunch of iterations, 17 or 18 iterations for this inner optimizer. Any guess why that might be happening? Well, what did we see last time in the linear mixed effects model? Sorry guys, I'm assuming that's stay up. How many inner optimizers did it take in the linear mixed effects model? Does anybody remember? Well, it took a lot less. I mean, and so the key here is that suddenly we're doing we're doing this generalized linear mixed model, and the joint log likelihood is no longer exactly quadratic. And so the inner optimizer is using the Newton method, and that Newton method is exact if the joint log likelihood is exactly normally distributed. So Caitlin and I were talking about this. What happens if your joint log likelihood is not normally distributed? Well, the first thing that happens is the inner optimizer takes a lot longer. So this is showing that where I started the model out, it was really far from normally distributed. It had to work a lot more than the inner optimizer. The other thing it's showing here is this U step. And there's no reason anybody would know what U step means without doing some digging in TND. But what U step means is basically it's changing the Newton optimizer. So the Newton optimizer at the value it's doing is so bad that it's intentionally not it's using this sort of quasi-Newton thing where it's taking smaller steps. And U step is a measure of how far the steps, what's the ratio of the Newton recommended step size versus the step size it's taking. And so the Newton step would be way too big, and so it's using a U step that's 1/100th of the recommended size to start with. And if you get a really bad model, this U step will go lower and lower and lower, and that's one symptom that TMB is just breaking. But in most models that are close to normally distributed, this U step will start out bad and it'll get better until it gets to close to 1. And when it hits close to 1, that means that this Newton step near the solution that matters gets normally distributed. And so, just to finish one more thought, and this is in response again to Caitlin's question about, why use the Laplace approximation when we know that a lot of joint log likelihoods are not exactly normal. Well, the key is that when you're really far away from your solution, it's more non-normal than when you get close to your solution in a lot of models. And so when you start out the model, this U step is horrible, but as we run the optimizer, we'll notice towards the end that this U step is always close to 1, that it always only takes a few iterations, and so the model will get closer and closer to normal when we get better and better parameters.
That was my question.
Okay, yeah, okay. We can then do the obj-gur, which only takes one step because it's remembering the solution for the random effects that it did before. And it only has one parameter. This model only has one. Is that right? Yeah, okay. Yeah, because it's a, I think I'm using REML. Okay, I'm gonna turn off REML. We can talk about REML in a later week. And I probably should strip it out for now. But if we turn off REML, we've got sorry about this. Yeah, we've got two parameters here. And so we can run it the first time, it still takes a lot of inner optimizer steps. we can get the gradient, and the gradient vector has length 2 because there's 2 parameters, and it's going to use that gradient to do the outer optimizer step using this optimizer. So again, the first iteration up here, the first iteration of the outer optimizer, it takes like 4 steps, and the U step is always at 1. But as it goes on, it generally is doing, requiring fewer and fewer inner optimizer steps as it gets closer to the MLE for the fixed effects. And that's one indication that this model is well behaved, where the joint negative log likelihood is close to normal around the MLE. And then you can extract the estimates. And if you compare the true values on the left-hand side, this is using the LME4 package, and this is using the template model builder estimates. These are identical to the 4th decimal place. Again, any guess why these might not match exactly?
We're using a different optimizer. Or,
Yeah, so LME3 did, I think LME4 is actually using the Laplace approximation.
okay.
I think LME3 did not, and they compare on weights. I thought I should look this up before I say too much, but I'm pretty sure that they switched the optimizer they're using. Does anybody remember who built this?
Yeah, it's definitely Bates.
Yeah, I think that they switched over using the Laplace approximation in this later version.
Yeah, because the estimates are the same when you set Ramel to false.
Yeah.
Exactly the same.
No, not exactly.
Well, they're really close. I mean, they're like
Much
within,
more similar.
they're to the 4th decimal place. I actually think that it's using the Laplace approximation, and TMB is actually just getting slightly closer to the optimum than the LME4 is. So again, TMB, because it has access to gradients, we can do the Newton step optimizer, and we can get the gradient to like 1 trillionth. Whereas I think LME4 is just giving up a little bit earlier. Okay, so what's it doing on the C++ side? Well, we've got the same block of code at the top that we always see. We've got this, I think that, can anybody summarize how data integer differs from data I vector and from data vector?
Data integer is just one value. That's an integer. I vector is a vector of integers. And a vector is just a vector of real or
Real numbers.
yeah.
So if you want like an integer for a site, or you want to specify some settings, like I gave you an assignment with multiple estimation models, you probably want to pass it via some data integer or data I vector. And then if you have some data, oftentimes it's data vector. And then we've got the parameters. In this case, we've got the mean and the log standard deviation among random effects, and then we've got the what will be random effects, the z sub z. We've got the joint negative log likelihood that we define by saying it's a type, and we initialize it to 0. And then a mixed effects model this is the same thing as a fixed effects model has, where you, in this case, I'm doing it where I calculate the predicted y value for every observation I, and I do that in a loop. And then I calculate the joint, subtract off the joint negative log likelihood for the data from a deep, Poisson distribution using DQuas. And then the new part of this model, in a mixed effects model, we've got this block where we sweep through the random effects and we accumulate the negative log likelihood of the random effects, given that they're mean 0, and have standard deviation equal to this log SDZ, well, or the SDZ, exponentiate that. And why am I passing the variable called log SDZ, but I'm exponentiating it when I'm using it?
Make sure it's positive.
Yeah, so that the standard deviations and variances always have to be positive, but optimizers work best if they have unbounded support. And so I have the parameter be in log scale, but I use it after exponentiating it. Why am I using, well, where is the log link of this model coming in the code? What line number?
24?
22.
Oh.
It's kind of hard to see the line number, but yeah, this line number. The log link means that I'm exponentiating, I'm doing the inverse link to the linear predictor. And this is a linear predictor because it's summing the intercept and the random effects. I exponentiate it. Why do I have to exponentiate? Why am I using a log link in this Poisson glim?
Has to be positive.
Has to be positive, the intensity function has to be positive. You can't have negative expected number of rabbits in your sample. And then, yeah, I mean, and that's it. So this is identical to a linear model, a linear fixed effects model, except we put in this additional block of 4 lines, including the comment, where the joint negative log likelihood is the sum of the log likelihood of the data given your fixed and random effects plus the log probability of your random effects given their hyperparameters. And that was, again, the definition of this negative log likelihood. Any questions about that?
What happens if you don't use the Laplace approximation and just try to optimize the joint likelihood?
Totally. So it's really easy to do that in TMB by just stripping out.
The random bit.
Yeah. So if I do this, if I change line 62 to not declare what's random, then the parameter suddenly is treating all of the coefficients as fixed effects. Does anybody have any hypothesis about what will happen here?
I know you hit the funnel problem.
What's that?
This goes back to the funnel problem that you see in MCMC they talk about.
Yeah, so again, I needed to remember to bring in my little drawing pad, MS Paint. So if you've got your y-axis and your variance, then you've got your negative log likelihood. If you are doing it correctly, which I'll use green, and you've got your negative log likelihood. If you're doing a mixed effects model, it's guaranteed to be, well, I always forget whether concave is curved up or curved down, but it's guaranteed to have a minimum. And so your MLE will be right here. If you do as penalized likelihood, which people did in fisheries for a long time and continue to do, then it will look sort of like this, where if you started out in this area, it'll go to a maximum penalized or minimum, well, the penalized likelihood estimate will be biased slightly low. And if you start at too low, it'll go infinite, the variance will just go to 0. And it can always achieve the best solution by just having the variance go infinitely close to 0. And to see why this is, you can, well, I mean, ask me later. You can derive by hand why this is by doing the Laplace approximation, where penalized likelihood is the same as the Laplace approximation, but just missing that determinant of the Hessian part. And so the determinant of the Hessian is guaranteed to be a monotonically increasing function, or monotonically, in this case, the negative log likelihood is a monotonically decreasing function. So the penalized likelihood is always guaranteed to be lower variance than the MLE. So if this doesn't clear it up, I have no, I don't know what would, really.
Isn't penalized likelihood in the sense you just kind of fix the variance of the random effects?
Well, so there's different, I think statisticians, I think people use these terms differently. I've been calling penalized likelihood both for when you fix the variances or when you try to turn on estimating the variances, but treating it all as fixed effects.
Okay.
So right now, this is what I would call penalized this is, I would call this penalized likelihood, where I've got the variance of the fixed effects, all the fixed effects, and the intercept are all being treated as fixed effects here. And if we try to optimize it, we actually get a solution, but this MLE of the variance is considerably lower than the true value of 1. And if we run it as a fixed effects model, my claim, somebody help me remember that the penalized likelihood came up with a negative 0.44. If we do it as a mixed effects model, the MLE is slightly higher. It's guaranteed to be, again, based on this sort of theory that we were just talking about. And if you did a simulation experiment, you could see that penalized local minimum is by a biased estimator of the variance. And then you could also just confirm, here I'll just try to prove it, that if this starts out too low, then you get stuck in that other part of the basin. So in this case, I'm starting out the variance. Starting out the variance at a really low number. And my hypothesis is that in this case, it'll just go infinitely low. Yeah, so it blows up. It blows up the optimizer when trying to do the standard deviation here, and because it gave an error, it just didn't even overwrite the previous object. So. Oh yeah, the Newton step. It's belonging to the Newton step. So in this case, I started out the estimate of that variance parameter at a low number, and it was, I think I already closed the paint picture I had, but I started out at such a low number that it just tried to make this go infinitely low. And because that's going infinitely low, it causes a problem in all of the other stuff that the model's doing. So it causes, the final gradients are not close to 0. And so in this case, it's so bad that the Hessian is not positive definite, and so it can't invert it, and so it's causing an error in the optimizer.
It's sort of like, basically you're adding unidentifiable fixed effects.
Yeah,
Right.
the variance, if you treat it as a penalized likelihood and you try to estimate the variance, you'll always get a bias even if you're lucky to start in the local area. And you're always guaranteed to have a better solution in that sort of variance known as 0 part.
Right, because you can just say all those random effects that are now fixed effects are 0 with variance that's exactly 0.
Exactly. And that's the tie to the funnel problem.
Yeah.
It's trapped in there. Okay, so that was a little detour. Does anybody else have any questions? I mean, the code's straightforward enough that I'm not sure what else to talk about.
I'm gonna take us back like 10 minutes. So for line 22 in the TMB code, the YPred, can you remind me where that equation is coming from?
Yeah, so a generalized linear model has these 4 parts. guaranteed to have 4 parts. It has a distribution for your response, and here we're saying that's a Poisson distribution. It has this linear predictor on the right-hand side. It has a link function, and it has a distribution for the random effects. And because we're doing a count data model, and so, like we talked about the first day, or maybe it was Tuesday actually, we probably want to use a distribution that's defined for count data, like a Poisson or a negative binomial. And those count data models require that the intensity lambda be positive. And so one way to make sure that this linear predictor, this linear predictor can go anywhere from negative infinity to infinity, whereas we want lambda to be positive. And so one way to do that is to use a log link, where we say that that this exponentiated is equal to the expected number of rabbits. And so that's sort of the model we set up down here, where the log link, log density follows, well, this is sort of a slightly different notation, but the linear predictor for log density is mu d. And that's the density at each site. And then we've got a Poisson distribution with that log density, with that density. And so, in this case, this is, again, this is slightly different notation, but this is saying the mean across sites plus the site-specific deviation from that mean exponentiated equals the density of that site. If we have extra time, I guess maybe that's a key, that's a clue to get into. Would people like to hear about REML or separability? I think this is relevant to separability. So in all of the models we'll be talking about, there's a bunch of different ways to parameterize them. So like, I think it was John, brought up how, I was talking about the benefits of maximum likelihood, and I want to talk about asymptotic normality and consistency. And John very correctly pointed out that you can transform the coordinates of the model and you get the same result. And in fact, you can kind of reparameterize the model a bunch of different ways and always get, and get the same model, meaning you get this parameter estimates that result in the same predictions for all the data. And so, maximum likelihood, we've always got this choice of a bunch of different parameterizations. And the key to making spatial temporal models work is using what's called separability. And so, separability is this case where we can divide up the model into a bunch of smaller chunks. So this is the joint likelihood, which I've factored into the probability of the data, given the fixed effects and the random effects, and the probability of the random effects. And a lot of models, we can break this into a bunch of smaller chunks. So, like in our rabbit example, can anybody explain how this applies to the rabbit example? The point is that I'm dividing this joint log likelihood into a bunch of different pieces of the random effect. So I want to divide it into a bunch of products that only have a single random effect, or a subset of random effects. So how would that work in the rabbit example?
Each location has a random effect, so each location is it's sort of independent of the others.
Exactly,
Given the hyperparameters.
Exactly. So and the hyperparameters are fixed effects. And so the joint likelihood with respect to the random effects, that portion of the joint likelihood can be blocked into a bunch of separable subsets where the value of the random effect at site 1 doesn't affect the joint log likelihood of the value of the random effect at site 2. They're independent. And independence implies that their partial correlation is 0. So there's a million ways of thinking about this. One way is about partial correlations. So if anybody's ever looked at, if you Google the term partial correlation, that partial correlation is where you fit a linear model and then you extract the inverse of the correlation matrix. And that's called the partial correlation. And if the partial correlation is 0 between two sites, that means the Hessian matrix between those two sites is 0. It's the inverse of the covariance matrix. And if that Hessian matrix is 0, it means that we've got something really easy about the Laplace approximation. It suddenly means that we don't need to bother with that part of computing the Hessian when we do the Laplace approximation. And so in the limit, every one of these random effects is independent of every other random effect given the fixed effects. And that means that jumping ahead a slide, what that means is that we can do the Laplace approximation for each site completely independent of every other site. And so that simplifies the computation the model has to do.
Is this, I think I'm missing something, but can you explain how that works? Because I guess the way I think about random effects is saying that there is some correlation between all of the random effects because they all come from the same normal distribution.
Yeah, so exactly. So they're all correlated because they're all arising from the same normal distribution. But given the value of the fixed effects, they're independent.
So given the normal distribution, if you took a random draw from that normal distribution, the next draw from that random normal distribution will be independent. Is that what it's getting at? It's like you're.
It's a little complicated because it's independence of the joint negative log likelihood. So it's not independence of the random effect given the normal distribution. It's independence given the joint negative log likelihood. And that joint negative log likelihood is the product of the normal distribution and of the data. And so you can have a model where every random effect is normally distributed, but they have, for some reason, they're sharing data or something. And that would mean that they're not independent in their joint negative log likelihood.
I think closer. I think you think.
Yeah, but everybody's intuition is different, and so it's hard to work with intuition without tripping yourself up. So I'm sorry I don't have better. But the key that I want to talk about now, and we'll use separability. I think we'll really get into separability starting in week 5, but I just want to introduce the concept now. So separability is about factoring this integral. So if we have a mixed effects model, we want to factor. We already took the joint log likelihood. We need to integrate it, and to do so, we factor it into these two pieces. But this is an integral with dimensionality equal to the number of elements that random effect. And integrals are really expensive. And if we have an integral across one thing, it's expensive. If we have 1,000, I have models with 100,000 random effects, and 100,000 dimension integral is just crazy. It's impossible to think about. It's really hard to compute. And so in the limit, if we had 100,000 sites we sampled for rabbits, we could, if we build the model wrong, we would be stuck doing 100,000 dimensional integral, or the Hessian matrix would be 100,000 by 100,000. But we know conceptually that the joint negative log likelihood with respect to the random effects can be split into a bunch of one-dimensional integrals, and that makes intuitive sense in this case because what's happening at one site, the draw for that site and the data for that site is totally independent of the draw for another site and the data for another site. Conditional on the value of the fixed effects that determine that draw of the random effect. So there's some link between the conceptual data generating process and the independence of the random effects that allows you to separate this integral into a bunch of smaller integrals. And that is called separability. And it also maps onto the structure of the Hessian matrix that we have to compute. So I'll just end with, okay, I deleted inlet, which is useful to visualize Hessian matrices. And then for some reason, inlet's not downloading well. I'll just, names, Hessian, I'm almost done with, we're almost out of time, so. You know you're getting into kind of something esoteric if you have to dig through the N slot in TMB objects, but obj and H. Sorry guys, maybe I won't, maybe this is one bridge too far. Well, I think I'll do this again sometime later. But the point is that you can check out what the Hessian looks like using TMB, and if that Hessian is sparse, that occurs because you've got a separable model. And a separable model occurs because the joint negative log likelihood in some way can be factored into a bunch of smaller pieces. So again, we'll use that again in week 5. It's not something you need to know right now. Any 3-minute question?
Is there such a thing?
Yeah. Okay, well, thanks. So homework's due. Arno, are you saying I can install it with bar inlet?
They have like their own CRAN.
Yeah, exactly, yeah.
You can't get accepted to CRANs.
Okay, well, thanks everyone. Yeah, chat more next time. Actually, I think this is it. Oh yeah, that's nice.
So why did people move from REML to this Laplace?
What's that?
Why did people move away from REML?
Well, so you can do REML with, I didn't talk about it today, but you can do REML using the Laplace approximation too.
Oh.
Okay, well, so I finally figured out the Hessian shit. But, so, that just for people that are still here, which we lost about half the people online that had stuck out through the break, but you can look at the Hessian matrix that TMB sees, and you can see the sparseness of it. So I, without talking about it, used a parameterization that was separable, which means that the value of each random effect has no effect on the joint negative log likelihood of the other random effects. Or another way of saying that is that the Hessian matrix, this matrix of second derivatives, is diagonal. And so TMB internally is detecting that that Hessian matrix is diagonal and encodes it internally using a sparse matrix. And so I've got 10 random effects, and the Hessian matrix is a 10 by 10 matrix. And it's smart enough to store it internally using this sparse matrix stuff, 10 by 10 sparse matrix of class P, S, C, blah, 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 where it's only keeping track of the diagonal elements, and this dot means that it is detecting that every off diagonal element is always gonna be 0. So this is TMB being smart enough to use the parameterization I gave it and automatically detect the separability of the parameterization I used. And that's why it ran so quickly.
So on your more complex FAST stuff where you have these correlation structures in the random effects, it goes a lot slower.
Yeah, but all of FAST is using 3 or 4 different tricks to make it separable.
Oh, okay.
So, starting week 5, I compare that you can get the exact same MLE using separable and non-separable parameterizations of the model, but the separable one runs hundreds of times faster.
So you can take some multivariate normal random effect and make it separable?
Some of them.
Okay.
Some of them you can, some you can't. Yeah, thanks everyone.